Everyone, sorry for the delay. So we are back on our barb-metal. So this is going to be the fourth video that we're doing of live solving barb-metal. And so if we look at our notes of where we left off here, so today's Wednesday. So we think we have an arbitrary read from plus or minus an offset through the thermometer read if we specify integer values here. And for this date, and we think we can have arbitrary negative writing. What I mentioned last time is the hard thing about this challenge is how do we actually let me reduce. Sorry, I got new mic stuff and I'm still dealing with it and messing with it. So let me see if that, yeah, there we go. Okay, I think that's better sound quality wise. All right. So cool. So, okay, now, oh, still there. So maybe you can tell I'm not a sound engineer, a fucking hacker. Okay, there we go. Those are much better levels. So, okay. So we think we can do that. One of the things I did earlier today was, so we have a way to talk to the program. If we recall where we were at, we could use this talk program, and that could use WebSockets to talk to the endpoint. The problem here is how do we then debug this? So I cheated by looking at the source code to see, but not the code itself, just the runner code of how this actually gets run and kind of runs itself. So as I suspected, it does use, it does use, whatchamacallit, QEMU system under the hood. And this is kind of hinted at by the term barb-metal here. One of the key things was if you just spun this up, you would see that it doesn't actually do anything or give any output. So I had to find the right set of commands here. I think one of the important things was this character device, making sure that it had a character device to look from. The other thing that I realized is this, so waiting for 32-byte payload sizes, I guess was stuff that I should have been thinking about here. But yeah, there we go. So if we go back to start, yeah, waiting for 32-byte, right, the payload size. That's interesting. Okay. Ready to receive. Huh. Okay, that's weird because I'm definitely not sending that. I'm sending... See, get car. Yeah, this is all right of how we thought about it. Okay. Well, read something. Here was the thing. Yes. So before the bootloader even went, we got called in this read something where we read, let's see, 49 bytes, and looking at, let's see, looking at the characters there. Yeah, 49. So our flag format that year had exactly 49 characters. So this is a hint that this actually, to me, should have been that a flag. So this was actually the flag here. So what it's reading first. So this is what I gleaned by looking at it, but I could have been smarter in understanding this. But just looking at how it was run, which you weren't given in the game, but you could definitely figure out. So we can cat the flag. So the input here is the flag and then the payload bin. And this makes sense. Okay, now I understand it. So it's reading the 49 bytes of the flag. So I'm going to rename this to be flag, which is going to be super important. We're going to want to read that out. And that'll be one exploit we can develop quite quickly to this. So we have that, and then waiting for 32-byte payload size. So we were wondering, if we remember when we were doing this, about why does payload bin, if we do hex dump to see, why did the start of payload bin start with not something that looked like, we knew that it started with, oh, that's right. We knew that the first 256 bytes were, which were up to here, these bytes are the signature, and everything after that is the payload. The problem is when we used just this payload, it wouldn't execute as Ruby bytecode. We actually had to, just by guessing, we guessed to go at the right offset here. I think the key issue here is these first 4 bytes are the size of the remaining bytes. So EE11, and let's verify this real quick. And if I say import pwn dot unpack as 64, and I'm going to import monkey patch, monkey hex. Too many monkeys. This is a cool Python package that makes sure all your output is in hex. So that if you say like this, it just outputs integers. Hey, Zion, good to see you there. Cool, we're just about to write an exploit. Maybe, I don't know, you should tell me, did you solve this or work on this barb-metal challenge in last year's DEF CON 2021? So let's see. Okay, so this should be, if I do pwn dot on 32 b 0 / xee 11 0 0 0 0. And that is, of course, now I actually want this to be the name of the file. So that should be, let's see, where were we talking to that file? Oh no, you're working on hyper. Oh, yeah. It's a pretty good challenge, especially that Broadcom challenge. So 4590, and if we look at the payload bin, right? So that was the thing that was really tripping me up earlier when we first looked at this. Is this was 4590, and of course now I actually need the calculator and do the hex conversion. 11EE, which is 4590. So that's the size. So the first byte is the size, and that's why we're looking at the size here. It didn't make sense because it said ready to receive 4590 bytes, which it was getting from standard input from the challenge, and that was actually already in the payload size. So the size is encoded in there. So now we actually know fully this payload size. We could probably then write payloads that mess with that size and do other kinds of cool stuff. Okay, but now we can run the challenge. So now we can, and we actually have, so we have an arbitrary read. So we have an arbitrary read from this buffer. And if I believe, looking at this, everything was kind of deterministic in where we were there. So we should be able to just figure out what the offset is to the flag, read these flag bytes out, and then just have an exploit that is able to get the flag. So let's try that. Now we're gonna have to debug this, so that's kind of the pain in the butt thing here. And let's see, from memory, so let's see, we had thermometer. So if thermometer read is where we're gonna go in, this is the function that we're gonna want to debug. Oh, I guess Zion, I can show off pwnda dbg, but let's see, will it actually work in a bare metal binary that doesn't have any offsets or anything? I guess we'll see. But what we can do is, so we're going to want to specify to QEMU the -s command, I believe, and this will tell QEMU to hang until it gets a debugger attached. And then we're going to want to, let's see, GDB. Oh, let me start up my server. We might as well see if we can get this to work. Plugins, decomp2 DGB. Okay, and I gotta look in my oh, I don't remember my ports for this machine. Let's see, 8081 is what I use. Okay. And I hate how in IDA that thing goes away when you alt tab over. Okay, 8181. Cool. So starting up the server here. Let's see. Hey, how's it going? Let's see. Okay, start up the server. Now I want GDB service. And I believe we could do target attach. And this is where, of course, you always got to Google for stuff. Okay, connecting to QEMU instance. Yeah, it's gonna be a remote target. Oh, good. I'm glad you like the things. Yeah, I highly suspect this will not work, Scion, but you know, I happen to QEMU system. Oh, I want GDB attach, not QEMU attach. GDB usage. Ah, there we go. Target remote. 1, 2, 3, 4, I believe, is the default port. Maybe not. That dash S. Oh, dash S and dash S. All right, let's try that again. Big S, little s. Hey, there we go. Now we're somewhere. Okay, so let's see. Interesting. Okay, all my Jeff stuff is breaking. That's cool. Oh, random question from David Terr. Does our research group at ASU have any postdoc positions? Yeah, I think we do. We're always looking for good people. Feel free to send me an email and I can. What is GF remote? Oh, I see. All right, so restart. Dun, 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 dun. Let's see. Elastic connect. Oh, nice. Okay, cool. How? Okay. Oh, I guess it's bad to show people that I'll just click on any link that you drop into the chat. Well, I guess I was looking at the right thing, so. Okay, good. A lot less information. GDB server. Oh, I see, I see. Okay, so we are doing QEMU mode. Let's see. Okay. QEMU system. You have to actually run Jeff remote? I mean, this doesn't make any sense. Okay. These docs are terrible. There we go. Okay. QEMU binary. Function not implemented. That's awesome. Good quality software right here. Maybe you're supposed to do QEMU user. Binary. Well, I might as well, you know, do it correctly. Hey, there we go. Like that. Now, do we dare? Decompiler. Sorry, I don't remember the command. It's been a while, and apparently I haven't done it in here in a while because it's not in there. Okay, there we go. Okay. Nope. Okay. Doesn't work. Oh, I didn't do IDA. No, still doesn't work. Okay, makes sense. It's a weird target, but that's okay. We can do it old school. Okay, so I don't need there. What I need is in here. Okay, so I want to get into this thermostat read function. And so 3D6A. I continue, and I should be there. And then this was read thermometer, so I'm going to say therm read day. Did not break. Not great. X dot 5I. Want to make sure I actually had the right place. No, I did not. Why? Probably because this is slid some amount. Let's see, what's my backtrace? Where I am is just reading input. X dot 5I. Okay. These are all functions that are called. Let's just assume that they're... I think I know where they are, but let's see. I don't think I can get the page mapping because it won't really do anything like that. Yeah, it doesn't really matter. Okay. So, yep. Thanks, Anne. Appreciate the help. 13D6A. Oh. Wait, this is at 13D6A, and over here it says 112D6A. Interesting. Which one is right? Okay. 2D6A. Let's pop over there. Boom, that's where we want to go. So we will want to set a breakpoint here. But of course, I messed up my input a little bit, so damn. I need to reconnect. What the heck? QEMU user, QEMU binary. QEMU user, there we go. All right, and then let's get that therm. Oh, sick. All right, now we are in this function. Allegedly, there is a way to do this in IDA, to connect IDA as a debugger to your process, but honestly, I've never done it, and I've just been kind of lazy doing it by hand. But okay, so we should see, this is what we really care about. So what we want to see is, right, what this actual offset is of this object. What we're going to do is we'll calculate the difference between that and the flag that we want to find. Actually, let's. So if I read that out. Yep, that looks like a flag to me. (000), that is the flag that I had. Awesome. Okay, followed by a new line. Cool. And that's at a fixed memory location, which makes sense because it's a bare metal challenge, so there's not going to be anything crazy. So we should see, as we follow here, we should see argc2. We should kind of see it follow through here. We'll ni it here, because do I care about this call? What is this call? I guess I don't know, and I guess I don't care. Okay. The decompiler gets rid of it. That's weird. Whatever. Okay. Stepping through, pushing EBP, moving the stack pointer to the base pointer, right? Setting up our function frame. I guess now we're after the call. Adding 10 to the stack pointer. Yeah, moving that. Compare. Great. So this is this argc check. So this is the argc check here. We should jump to 1112 dad. Which actually is not, what is that? Well, all right, so now, yeah, cool. So now move args plus EBP, dereference that, move that into EAX. Then EAX, I should probably be keeping track of what is in EAX. So EAX is, let's see. Oh boy, okay. So we are here, args. Right, so we're getting, okay, we've got to go backwards. Where's the actual dereference, like the final thing? V3 is equal to that. Okay. Let's see, at the end of this block. Oh yeah, we do the test. Okay. Okay, so that's everything before there. So this comparison with var_c, this must be args2. Right, because that is moved in here. Compare that with 0. Compare this with EAX. EAX plus 4. Arg, getting args. Oh god. Okay, getting args. That there. And then let's see. EBP args there. Add 18 to args. Dereference that. Move it into EAX. Copy that into var20. Move that into EAX. Move EAX into dereference EBP plus var4. Okay, what I'm really looking forward to is what is just the actual dereference. It's probably going to be close to the end here. Let's see. EAX. There we go. Dereference EAX. Move it into EAX. Cool. Okay, so I think we finally found here. I guess I should have set that thing to be 0, and that would tell us the nice offset, because that's a good trick. I can use it later. Okay, so x20 I $sign e. It's not RIP, EIP. Okay. Are we on a? Okay, I got lost with where we are. So let's do. What I want to do is here, and I want to find out what is EAX here, and we'll set up therm to be 0, and that will tell us way more information about what we want to do. Okay, so it's 112 DEA. Okay, but I am going to disconnect from it. Okay. Go. Okay, now this time I want to send therm 0. So read day 0. I can't do that. Invalid day. That's annoying. I haven't figured out how to send more data to it. That's really annoying. Okay. It's okay. Boom. Disable 1. And okay, I need to attach. Now I can set the breakpoint. Oh, that's right. There was that check for like. Okay, there we go. Reading day 1. Move ZZ EAX. So let's look at what EAX is. 248 A26. Okay. So that's where that is. So let's see, I should be writing these down. Okay, so Thermary day 1 read from this. Moving AX into A2, and that's what eventually gets sent back, variable A2. Okay, that makes sense then. That's why it's always the last byte, this AX. So, and let's just verify our assumption here. So why don't we do 1, and we can do, I don't know, 10 and detect the difference between them. That would be pretty cool. Okay. Okay. Great. Okay, so now we have that, and let's check out the difference between them, because I am, as we all know, lazy. Who wants to like manually do math? 12, so the difference there is 12. OX12. Okay, question was, can I do, I don't think I can do negative numbers. I mean, I think I can, but I can't remember if the bytecode actually strips that. But we can set a very large number that causes it to wrap around. Just a second, I'm going to get some. All right. T acquired. Okay. It is weird that difference of 9. Let's see. What's this? Calculate this. 12. That is 18. Oh, divided by 9. Right. So a size 2, because we can get 2 different bytes depending on that last one, depending on if we do day or night. So that kind of makes sense that we went 18 bytes, which was 9 times 2. So I think if we want to target where the flag was, G flag. Oh, hello. Okay. All right, I guess how, if I want to get there, I'm going up there. But that's not right, because if I do this, oh, there we go. Shit, okay. So 65DA, it looks like, is, shoot. Just deleted it. Okay. So offset is 65DA. So if we then divide it by 2, 32 ED. So OX Should start to read from the flag, which is 13037. All right, let's try this. All right, same breakpoint. And so we want to try therm read day. Oh, I guess it'd be better. The other thing I need to do is figure out this loop. I'm using this janky cat, the file flag, and then payload bin, and then dash, which works for one thing, but then it says resource temporary unavailable, so I'm not really sure why it's doing that, but just to provide input to this guy. All right, let's see what EAX is here. Ooh, it's real close, isn't it? Or too far away? Let's see. 2-4 is correct. I think we need one more. 2-4 EFFE, which would be like right before this. Oh, EFFE, which actually is here. It looks like that's a stack. That's weird. Well, that's cool. I guess we can then do exploits to read and write from the stack. Okay. And 24 EFF. Great. Okay. And okay, so let's do one more. So here, man, I'm picking up good habits, I guess, when I'm streaming, because I usually don't take these kind of notes when I'm deep in a CTF, but I think it's actually great and really good practice to do that sort of thing. Okay, so let's try that. And I'm not going to worry about that right now because I got a good flow. I just want to see that this works. Try. There we go. That's our flag, ladies and gentlemen. Yes. All right, so that should return bytes of the flag. I guess LZCNT, the creator of this challenge, who I talked about this, was correct. This is a pretty good, easy challenge, so a good one to do for this kind of streaming. Although it did take me, I don't know what this is, the fourth stream, so 3-4 hours to get here, but learned a lot, and that's good. Okay, so now let's, this is fantastic. So this means what should be now inside EAX should be 3030. So it's 2 bytes of the flag, but then it moves AX into there. So just the, I guess, what does it move? The lower bytes? I guess we'll see. Is it moving the whole thing? Is it, I'm doing too much. I always got to refresh myself and look here. So 1, 2, 3, 4, right? 32 bits, 4 bytes. And so maybe it just says 2 bytes, but then that makes our job a lot easier. So if we then continue this, it says day 48. Okay, so it did redact, right? Because it only returned 48. If we look at 48, that is hex 30. And this, ladies and gentlemen, is exactly the flag that we're looking for. Ah, sick. Okay. So we should be able to read the flag pretty quickly by just writing a script to do this. And let's see. Since we have a Python guy to talk to it, I guess it shouldn't be too much trouble to turn that into an exploits. And I guess I don't need anything else from there, but let's see, think. F. Cool. Okay, so this means I don't have to fix my debugging situation right now. Let's just use this leak and pop out some flags. Cool. And again, just kind of talking about how we'd approach this in a real CTF, we'd probably at this point, once we understood the bug, we'd work with somebody else and have them start to patch it. But again, this one, as we know, the only file that we can patch is payload.bin, which is the Ruby bytecode, and we have to bypass the signature check. So we'd have to find a bug in the signature check in order to patch it. So that's pretty cool. And we can probably just bounds check the size there to not allow such a large read. Okay, great. So let's see. We have talk.py. Right, this was the interactive bit that went with our input. Man, but it does do all that stupid stuff for us. God, I guess we can be super janky and just write an x.py that was this acceptable? I guess I don't even need to use pwn tools. I'd use what, pexpect or something, but I would think I could probably use pwn tools for this. Okay, so I'm going to be cheesy and I'm just going to not implement my own. So I'm just going to actually just call this talk.py script and talk to it as if I was typing shit in. But that way I don't have to mess with the talk.py script. So p.process. See if this works. Okay. Oh, pwn tools. Let's see, tubes process. Always gotta read the docs. argv, list of arguments passed to the spawned process. So I think if we do something, goes a little something like this. Okay. Of course, Python doesn't exist. /Python. Sick. Okay, so now we can talk to this just like it was. I think we may get some weirdness, but that's okay. So let's see. Okay, receive until there. And okay, so read out the flag. I guess we need to figure out if we need to debug to figure out if day and night returns that next byte or not. The problem is our flag is kind of lame, but oh, I guess against this target, it's not lame. Or we can look in our trusty IDA and maybe just reason about it. Do we like reasoning? Let's see. This is where it checks high byte into there or low byte. I should just figure out which one this goes across and then right, that's why it's stored AX and then later in each of those branches. So let's do that and figure that out because we'll need to do the leak it out in order to know which way we need to go. Nope, not GDB. You are QME. This showcases the importance of how important it is to actually be able to debug things. It can be a real pain in the butt if you can't actually debug the challenge. So that setting that up in and of itself is a useful skill to have. Okay, let's see. System there. What was I doing? Debugging. Back on that debug. Okay, GDB service. Okay, Jeff remote. Okay, and then now let's debug at let's see, it was day and night. Let's try it. Did hit there. Okay. Okay, we're definitely getting the right address. That's great. So that's good. And next instruction, move that into 2AX. Okay, now it's dropping into DF7. So this is the day branch. Oh, I should annotate them. Let's see. So this is jump if not taken. So this next one should be DF7. Yes. So this should be intercomment. This is the night branch. All right, night branch, and that means this should be the day branch. And I'm not sure if the comments actually propagate to the disassembly, but they should. Okay, so I can tell by like putting it in here inside the night branch, and so I can then just say night branch. And okay, but it's reading it as a God. Okay. But it's reading that value. It's treating it as like a short, right, to get this in 16. And then it gets the high byte from there. So I think we're going to have to mess with the Indianness a little bit just to make sure this actually pops out correct. But fundamentally, it doesn't matter. They each get that 16 byte value. I guess I could just recreate it in Pwn Tools and then just let Pwn Tools figure out the Indianness, which is always. Now, if I don't know the binary, I'm going to need to set the Indianness. Pwn.context. Let's see. Let's set the architecture. Yeah, there we go. And is it I386? There we go. I can never remember. All right, there we go. Okay. So got those, and I will also need P16s and U16s. All right, so now let's get that flag. So flag length. Let's see. I think it was 48 straight characters. Okay. In range. Okay, so we'll do this many times as the flag length. Let's see. Equal to B. Okay. Oh, let's see. So looping over that, but the real thing. Okay. Divided by 2. I'm going to divide this by 2 because I need to read a day and a night. And my start offset. Okay, so I will first want to send line. Let's see. Oh, I do want to know where I am there. Right. So I plus start offset. Okay, so first, let's see. In the day, looking at IDA, the day branch is the low one. So let's just start with that high byte. And then I'm going to append them together, interpret it as a base 16, and then put it in my bytes here. Okay. And con.receive until. And what I want to know is, yes, it will say day, and then RE, good. I have the, okay, RE dot, not match. I want to search for the pattern of day, followed by space, followed by plus. And of course, these are bytes, so we need to tell it that. Okay, so re.search, does that look correct? Search for pattern and string. Flags, don't need any flags. Let's see, match.group 1. Group 0 is the whole match. Group 1 is there. We know that that should be in here, so we're okay. It's CTF. It'll just blow up if that actually is not present, but we really just don't care about that right now. Let's see, results, and then leaked day value. In result, okay, so that's the integer there. And then let's do the same thing with the night. If I needed to, I would write these into functions, but I really don't need to, so I don't really care. Okay, let's see, just to double check if I have something like this. Int works on byte strings. Yes, it does. That's so nice. And then, okay, so now I have the, let's see, I can recreate this, this 16-byte value by doing something like this. Like I know the night is the high value, so I can do, is value left shift that by 8. So that's going to take the leaked, let's see, leaked night is the high one. Take the leaked night value, shift it over 8 bytes so that the lower 8 bytes are all 0. And then we're going to XOR this with the leaked day value. And that should be this value that's actually stored in here, which should be the, so flag value should be, let's see, and if I have pwn.unpack 16, pack it as a 16. Yeah, okay. Oh, I feel like I'm still going to mess this up, but I think that's good because I've extracted the value there. Yeah, and reading that value as a 16-bit as a short in her, when we read it, yeah, should only read in that much. So let's see. So pack this into a 16-byte value, flag value. Let's see with a flag value, and then all right. I don't really like just trying and YOLOing exploits, but sometimes I do. Cool, there we go. All right, flag length was 48 divided by 2. Float. Object cannot be interpreted as a number. Okay, we definitely don't want this debug crap, so let's turn that off. Oh, Python, you used to be so nice. You could just... Hey, that looks like a flag. All right. Let's see. Huh. Oh, yeah. This is the one that I have going. Okay. Well, that looks right because there's a 1 at the end. So if we got these values wrong, we should have seen them flip. Let me fix some of these errors here. So this Man, I never know if it's encode or decode or... Hey, I did guess it right, though. If you can see here, our flag value is kind of stupid. I should just be able to call .decode. And I don't need connection interaction. Now, the reason why I don't need interaction or anything, A, because I looked at the flag, and B, we probably want to have this exploit be thrown into our team's shooter system. Sweet. All right, so we got our local flag. Let's go and see if we can get the remote one. What am I going to do with you? Let's see, I'll probably just knock out the screen while I do this because I don't want to leak the flag for here for those that are trying this at home. Let's see. Okay, got it there, got it there. Yeah, but I want your flag, buddy. Okay, so I'm gonna kill my desktop. Let's see, just giant black screen. Of course, I didn't actually like prepare for this at all. So let's see, opt in, spawn a server. You can also kind of thinking about this challenge, it's kind of interesting now because it's this would be difficult to detect from a network level perspective that you saw the flag leaking because it's just because it's just a series of commands that each leaks out a byte at a time. I'm actually very skeptical that that thing actually worked. But let's see. I should create different scenes or something in OBS, but let's see. Come on now. And, you know, we'd probably weaponize this a bit more, put in... Yeah, great question. So now after getting the flag, how we go about patching the program. This specific program is actually a big pain because it's running Ruby bytecode, and specifically in this challenge, the payload that you can patch has a signature check at the top. So the first, I think, 256 bytes or whatever are a signature that there's a hash and stuff compared with a second with your actual payload. So to patch this, you can only patch the payload.bin, which is the Ruby bytecode. So you can upload your own one, but in order to actually get your patch deployed, it needs to get around the Ruby this signature check. So we would to even patch this challenge, we need to have a different vulnerability. I thought this one would be a cool one to show patching, but it's it's more annoying here. All right, it says loading the container, and I'm getting status updates. Always a good sign. Let's see. I really want that flag. Yeah, so it's interesting this if you thinking about this challenge, right? So it's other ways that it's interesting. There were several different layers. There was the web interface. There was the binary that we were given, which is just a bare metal x86 system that is a compiled version of mrubyc, which is running bytecode that is signature checked. And so there's a lot of different levels, but the nice thing is because we're using like raw code here, we can fundamentally because we're running in bare metal, there's no ASLR or no anything like that. So we don't have to deal with any of that kind of stuff. So let's see. Okay, loading the container, still loading. I'm sure it's super exciting looking at a floating head in a corner, but yeah, and the other thing is, so this was one vulnerability through this read function. We also saw there's a vulnerability with writing. So what we could do is then use the write to write onto the stack and write kind of our payload, write some kind of ROP payload or shellcode or something. I think this would be pretty easy. We could just find an executable page, write some code there, I wonder if we could write Ruby shell code and a bytecode and have that be just executed by the interpreter. There's a lot of different options here of ways that we could exploit this service just with these two things, remember? And this is the other interesting thing. We only actually looked at the at one. Okay, there we go. It loaded. We only looked at the thermometer, so I'm sure there's vulnerabilities in the other services that may be more or less complicated. Okay, so I'm going to plug in my IP address that I was given. The port's the same. I'm going to run it. Starting local process. And gave me the same flag. Oh, that was correct. Okay. Great. All right. Well, got that flag. Why is it the default flag? That's so weird. I'll have to talk to people and try to get that fixed. But sweet. Okay, so now popping this back in, proving that it works locally. Cool. So now we have a leak to leak out the flag. Like I said, other things that we do here, figure out how to patch it. But again, so I was talking about it earlier. I'll go briefly back through this code of the start function. So yeah, looking at start. So remember, there was this verify payload function, and this is the one that you actually have to break in order to patch the challenge, because we can only patch our payload. And so we need to do that. And then we'd also look at, there may be vulnerabilities in the alarm function, the smart speaker function. So I'd guess that there's a couple other vulnerabilities. We could also weaponize the writing functionality. The other interesting thing is we can only patch the Ruby bytecode. So somebody would have to figure out what is the new Ruby bytecode that we want to deal with. So that's kind of interesting. So yeah, all right. So we got the flag, solved the challenge, and I won't be on later this week, but probably next week I'll be back and we'll look at some new challenges, maybe some of the ones from Seesaw, because I know those were some cool ones there. So yeah, if you've been watching, thanks. I appreciate it, and I'll see you next time.